All right, we're going to talk about approximate methods. So this is what your computers are doing, obviously, because it's very necessary once we get even to helium or hydrogen molecules. We cannot solve the quantum mechanics exactly. So we must be using approximate methods when we're doing these labs with ethane and your current project. All right. They can be, even though approximate, be very accurate, especially for smallish systems. You can get 5 significant figures, which is good enough in most cases. Um, and computational chemistry is an active area of research, even in experimental groups. Some of you are going to graduate school, and you might be going in organic chemistry or inorganic or analytical, and you still will have either collaborations with computational chemists, or you'll do computational chemistry right in your group. So it's good that you're getting some exposure to this because you might be doing it in the future. So I'm going to talk about the main workhorse today. That's the variational method, and we'll talk about a few other methods, perturbation theory and density functional theory later. But today, the basics of the variational method, the principle behind it. The main thing is this is used to help find an estimate for the ground state of the wave function and also the ground state energy. So let's suppose we have some system. There's a Schrodinger equation, but psi and E are not known. The Hamiltonian is known. So it's kind of the usual case. We know the Hamiltonian just from the physics of the system. Let's suppose we imagine a set of orthonormal psi n's that we can use to build a guess for psi. And initially this seems pretty silly. Like if we know the set of eigenfunctions, why are we building a guess for the ground state? But just trust me here, this will all make sense in the end. Okay, so we're going to say that our wave function is approximately some trial function, which will be the sum over all of the wave functions for quantum number n, each multiplied by a coefficient for each quantum number. So these are just basically constants, which could be small or large depending on how important that particular wave function is in the sum. But we know that they're orthonormal, so in other words, if you integrate psi star n, psi n prime, if n and n prime are the same integer, then these two are the same and you get 1 because it's normalized. But if they're not the same, you get 0 because it's orthogonal. Okay. So this kind of sum is just called a linear combination in math speak. All right. Now we know for the ground state that h psi 0 is equal to E0 psi 0. Remember, we still don't know what these actually are, E0 or psi 0. All right. Now we could multiply both sides by psi star 0, and we could integrate, and because of normalization we know the denominator is going to go to 0. We can do the same thing with our trial wave function. So E trial would be equal to integral psi star trial h hat psi trial dv, and then the denominator. This denominator is kind of like a normalization constant. Now I'm going to plug in the linear combination for our psi trial. So now we have a sum over n cn star psi n star h hat, and then we're putting in n primes here because sometimes n and n prime will be the same and sometimes they'll be different. Same thing in the denominator. Then we go ahead and operate. So what was h hat operating on this sum? Now the h hat is gone and is replaced with e sub n prime because we did all that operating. Same thing. Oh no, there's no Hamiltonian in the denominator, so that didn't change. All right, now we're just going to sort into terms. We'll have all the terms where n is equal to n prime, and because of normalization, all of those integrals will go to 1. And then we'll have all the terms where n is not equal to n prime, and then all those terms will go to 0. Same thing happening in the denominator, so all the integrals are either 1s or 0s, and we end up with E trial is equal to sum over n, Cn star Cn En over sum over n Cn star Cn. Now, we have an expression for E trial. Fine. What if we subtract E0? And I know this seems arbitrary and whimsical, but just let's stick with it for now. This is still unknown from both sides. Okay, so now we have an E0 for each of these terms in this sum. But now if you think of splitting this out, it's divided by the sum of all of those coefficients. So that's like your normalization. So each one of these in the numerator is just a fraction. And we know that E sub n minus E0 is greater than 0 for all n because E0 is the ground state. So each term on the right-hand side must be greater than 0. Right? We won't have any negative terms in here. So then the total on the left-hand side must also be greater than 0. So we just proved that E trial minus E0 is greater than 0. Okay, so now that's for any psi trial that's a linear combination of the psi n's. Now this is just a math thing that I'm not going to prove to you, but psi n, this set of eigenfunctions, if it's a complete set of functions, then we can build any arbitrary function from a linear combination of a complete set of functions. So we just generally prove that for any arbitrary function, the E trial that comes out of it will be greater than the ground state. Now this is the genius of the variational principle, because now E trial is greater than the ground state for any function. So what can we do? We can choose any psi trial and know that the E trial we get out is greater than the ground state. I just said that same basic thing 3 times because it's so important, I guess. I don't know. It's still sinking in, maybe. So now to use the variational principle, this means we can choose any crazy function with a variable parameter, and I'll talk more about that and give an example, and then we'll minimize it. And then the E trial with respect to those parameters, as we get better and better, closer and closer to the true function, the minimized E trial will get closer and closer to the ground state, but never go below it. So we have a lower bound. And then we'll assume that the wave function is also getting closer to the wave function ground state, although there's a little leap in there. The biggest downside of the variational method is it tells us nothing about excited states. This is only helpful for the ground state. Okay, let's look at a couple examples. So for the non-relativistic hydrogen atom, we can actually solve that exactly. So then you're like, why are we using an approximate method? But it's still good because we can test if the approximate method works. Okay, if we know what the answer should be. So this is our ground state wave function, ground state eigenfunction, and we know that that's in your textbook. I don't know why, but this lowercase m looks weird to me. That's just the mass of the electron. Okay, let's pretend that we don't know what the ground state wave function is for now, and we'll try a trial function. And we're just going to have just one term in our trial function for now, instead of a linear combination of a bunch of terms. Notice the functional form is different. So in the hydrogen atom, this is called a Slater orbital, where it has e to the negative r to the first power. This is e to the negative r to the second power. This is called a Gaussian. All right, alpha is some constant, so adjustable parameter. We can plug it into our formula. E trial is psi star trial, h hat, psi trial, dv, blah, blah, blah. So dv, we need the volume element for spherical polar coordinates. So we've got sine theta d theta, we've got d phi, we've got r squared dr, and in the middle we've got our trial, psi star trial, psi trial. It's not complex as far as we know. We got the h hat there, we got the denominator. Okay, we know what the h hat is from our textbook. And then it can be shown that, and you'll do this in your next problem set. Go ahead, plop the Hamiltonian in there, do the operator. The angular parts all cancel because there's no angular dependence on a trial function. You get E trial coming out. To minimize it, to minimize any function, you can take the first derivative, set it equal to 0, solve for the root, and this is what you get for the alpha. Plop it into here, and you get E trial is equal to negative 0.424 times this collection of constants. Compared to what we had up above, this is basically negative 1/2 times that same set of constants. And so we see negative 0.424 is pretty close to negative 0.5, but it is greater than, so that does give us a good estimate, and as expected, it's greater than the true ground state wave function. All right, now in practice, we would use a whole bunch of Gaussians, so we have this sum. If you go up to 2 Gaussians, then you get negative 0.485, 3, negative 0.4969, 8, negative 0.49992, 16, negative 0.49998. So you can see how quickly you can get to 5 sig figs with this method. And then in theory, we can't really do an infinite number of Gaussians, but if we did, we would get the right answer. I think that's provable, but I don't know how to prove it. Anyway, you math people could do that maybe. Let's look at just another example quick, and then I'll be done. Harmonic oscillator, here's a Hamiltonian. We also, again, know the ground state. We know this one actually is a Gaussian, so it's shaped kind of like that for the ground state wave function. Let's try a trial function that is a cosine. That's also a function that has curvature downward. The shape isn't quite right, but it has the same basic idea anyway. We need some boundary conditions here. Negative pi over 2 lambda. Lambda is our variational parameter, and x is in between these two bounds. And then we get the right shape. Integrate. These are our integration limits set by the limits in x. And then it can be shown that, and that'll be in your next problem set. The minimized E trial is 1.14 times 1/2 h bar square root k over mu, compared to the true ground state is 1 times 1/2 h bar square root k over mu. Not bad. And again, the E trial is greater than the E0. All right, that's the basics of the variational method with a couple of examples.